So we heard a bit this morning about doing data-independent acquisition, and my talk is going to be about monitoring phosphorylations by targeted proteomics. I'm going to talk both a bit about SRM and SWAT type of data, but I will always try to keep it general enough to be applicable to both. And this is because some things that we do in phosphorylations or any type of other modification are a bit different when we look at specific peptides versus when we look at proteins. So till now we were doing tutorials at the protein, trying to quantify different proteins, and sometimes we're not interested in the level of a protein, we're interested in the level of a specific peptide, for example, a modified peptide, and then things are a bit different. So I'm going to try and bring up some considerations when you do targeted proteomics on modified peptides, what to remember, and I'm going to emphasize everything on phosphorylations, where I personally have the largest amount of experience compared to other modifications. So the first things first is how to add the modifications. We already did it right at the beginning, so I'm just reminding you. We have this tab where we can add modifications. We can add phospho on ST or on Y, and then if we want to include also the neutral losses, so the loss of a phospho group plus the water, then we need to also specify this in Skyline. Once these modifications are added as variable modifications, we can then insert modified peptides. The way to add the peptide is first, you can import it. If you want to import, you can just paste a list of peptides, as we've shown you in insert inside the edit. And if we paste the modified peptides, we can simply specify in brackets plus 80, and when we've set up the modifications correctly, Skyline will recognize that this is a phospho group, and we'll add this into our list of peptides on the left of the Skyline view. The other way that we can also do is start from a certain sequence, and then we can modify within Skyline. I don't show you this now live, but here you have the option to do modify, and then you can do a variable modification here. There's kind of a drop-down menu, and you can add these modifications or change them or move them according to whatever is your need. So this is another option already within the Skyline view when you have already your peptides. This sometimes happens when you already pasted your sequence and then you go, oh no, I made the mistake, I put it in the wrong place. You can also move it when it's already in Skyline. And the third option, which again I don't show you live, but you can go to a spectral library in view, and you could go to libraries, you can pick a peptide you find there, and you can add it as a modifier. You can add the peptide there. So there are different ways to paste in phosphorylated peptides. This, of course, applies to any type of peptide. It's not only about phospho specifically. So that's just to get you on how to get the phosphorylations into Skyline. Now, there are different considerations that we apply when we think about quantifying proteins, and they vary a bit when we think about quantifying phosphopeptides or modified peptides in general. You already saw a similar slide from Edward, you saw a slide from Tina. We try to apply different considerations when we try to choose proteotypic peptides for quantification of proteins. And in phosphorylations, many times it's exactly the other way around. We're interested in a very specific phosphorylated peptide. We want to target a specific modification, and we then need to consider also other modifications that might occur on this peptide. We need to consider the length of the peptide that might not be ideal, and so on. So we need to be much more flexible with all these considerations. When we were quantifying proteins, we could just dismiss this peptide, choose another one. When we're quantifying phosphopeptides, we need to take these things into account. Another very useful thing is then, once you've chosen your peptide of interest, is to also try and see, was this already previously seen by MSMS? There's all sorts of data repositories out there about previous studies from various groups, from large-scale phosphoproteomics. And I always, when I work on a certain phosphopeptide, I just first go and have a look, did anybody already see this phosphopeptide? Or am I going to be the first one to try it? So of course it's very nice to try and detect peptides that have been seen many times. It increases the chance that you are going to see it, and maybe you can also see some information from these databases if it was seen in a certain cell line or if it was seen in a certain type of enrichment procedure. So try and gather a bit of information about what you're trying to detect when it's a very specific application. What is very important to remember is that, and I will keep coming back to the point, is that when we're trying to detect a phosphopeptide of interest, it's very sample dependent. So just like a protein, also with a phosphopeptide, if you're not working within the right conditions, you might not see this phosphorylation because you just didn't enrich it or whatever. And when we talk about peptides, till now we were working with this workflow of having a library and having some sort of peptide identification. We trust the identification with a certain score, and then we continue to make an assay out of it. And when we talk about phosphopeptides, there's another element, and that is not only just the identification of the phosphopeptide, but also the identification of the right site. And so the localization of the site in phosphopeptides is very important when we know which residue is phosphorylated. And this is not always an easy task. Actually, in most cases, it's quite a complicated task. And let's take a I'm going to go now through some examples to really stress this point. So this is a project that Tina was working on. She was working on 2 proteins in yeast, and then she searched the data that from phosphosamples that she made from yeast extracts and tried to identify a certain phosphopeptide of interest. And in this case, as you can see from the search engine, you get a list of phosphopeptides. They have a very high probability. Some of them have 1 phosphorylation or 2 phosphorylations on different sites or in different combinations of sites. And in theory, all of them look pretty nice, and we actually don't know. Just looking at the list, we have no idea. So sometimes we try to use another tool that will give some sort of site localization score. Maybe you've heard of some of them. But at the end of the day, we're not necessarily going to always be able to get a very good score for this localization. And what will happen now is that if we now make out of this PepXML file a library, all of these peptides will be in our library. And now we need to decide which one we want to target, or maybe we want to target them all. But we need to always remember that each one of them is considered as a separate entity, because some of the transitions will be shared and some of the transitions will not be shared. And Skyline takes each one of them as a separate entry. And what we also don't know is, are these just misassignments? So this is a problem of the search engine, or are these real different phosphorylations? And sometimes in some of these it's phosphorylated on this residue, and in some of these it's phosphorylated on this residue. We a priori don't know this knowledge. And when we want to select transitions in SRM or extract transitions in SWAT, before we were looking at transitions for sensitivity and selectivity in trying to describe the target peptides of interest. Now we also would like to have selectivity for the phosphorylation site. So we are not only looking at transitions that are always the most intense, but sometimes we might select a certain transition that is not the most intense one, but maybe it is very useful for the localization of the site. And these things we always need to keep in mind, especially when we're doing SRM and we want to select the transitions before, or if we're doing data-independent acquisition when we extract our transitions. So let's do some selection of transitions. First, we selected the peptides of interest. We're going to look through this example that I showed you before. Now we're going to consider the case where there's only one phosphorylation, so one type of phosphorylated peptide. Here there are 5 different options. Here there are 3 different options, and we need to select transitions for these. And let's first look at all the Y and B ions, and we use the filter settings in Skyline, and we'll get a list that is kind of reorganized like this. And what you see is, you've seen a similar slide already in Rudy on the first day, that there are certain transitions that are shared. So no matter what is the site localization, these are always useful because they are fairly early Y ions, and so you will see them in any case. And later on, the bigger Y ions will depend a bit on the site localization, and then there are different masses. So some of them are specific to a form, and some of them are common to a form, and we can use this information. But we can basically, what we can basically do is think of some sort of combinations of these things, and we're going to get back to this. Another thing that we, in this case, don't look at is that there are also the possibility of using the neutral losses. So here we extracted only Y and B ions, but there could be also the case where we would extract the same ions after losing the phosphosite, and these sometimes are actually very intense transitions. So I show you here a peak group where all neutral losses are included, and you can see here the intensity. Here I removed from this peak group all the neutral losses all the fragment ions of neutral losses, and the intensity is lower. So for quantification, sometimes neutral losses are very useful, and sometimes they are very systematically higher and more abundant than the same transition that hasn't lost it. So if you would, I don't know if you could see, but maybe in your printouts, if you would follow the pairs of ions that have a neutral loss and don't have a neutral loss, it is consistently the case that for this specific peptide, that the neutral loss transition is higher than the non-neutral loss. So sometimes they're very useful for quantification, but there are two things that you need to remember when using neutral losses as transitions. One is that they differ a lot between machines. So if you're going to use neutral losses and your library comes from shotgun data, sometimes on the SRM machine or another machine, if you do data-independent acquisition, if you move between machines, you might get very different relative intensities. And I give you here a very pronounced case where the neutral loss is the most abundant in the Orbi data and has a very different relative intensity when you go to the SRM trace of the same peptide. And the other thing that you need to consider is that neutral losses can happen in different combinations, and there are neutral losses of the phosphor group, but also the loss of water groups from serine. So if one option is that we have a phosphorylated serine and it loses the mass of 98, and the other option is that we just have a serine and it loses the water, that would be minus 18. But if we have a certain peptide and we think the site is localized here and we take a neutral loss, the Y7 will have these masses after the neutral loss. But what can also equally happen is that the phosphorylation was actually here, the Y7 lost only a water group, and we would get to the same combination of masses, but we're actually measuring something else. So when you're considering to use neutral losses, please remember that they are not very useful for site localization unless you start to consider all possible explanations for the neutral loss, but they can be very useful for quantifications because sometimes they're very intense. So we talked about very briefly selecting those transitions that might be useful for localization. We can also use neutral losses for quantification, but using them for localization is a bit problematic. Now I'm going to talk about when we actually go to the machine and we start to do the measurements. I'm going to talk about two main types of workflow. In the first workflow, we have a reference-based workflow where we basically have, for example, synthetic peptides for all these phosphosites that we're interested in. And in the second workflow, I'm going to talk about the cases where we only work with shotgun data. I start with the reference base to make certain points very clear, and then when we move to the shotgun data, you will see why it's very important to take these things into consideration. You'll see it in a moment. And the concept I'm going to talk about is that when you look at site localization, it is not only about the transitions that you measure, but it's also about the retention time at which you measure. And there's been this concept circulating that in many cases, not all cases maybe, but phosphopeptides can also be separated at the level of retention time, not only at the level of transitions. And the idea is that if we have some sort of site that is phosphorylated at 3 different places, there will be maybe differences in relative intensities, but also differences in how they are separated by the chromatography at the retention time. And then we can use both the information on transitions and the information on retention time to try and separate these different phosphoforms. I'm going to always use the word phosphoform as a way of saying the same peptide but different phosphosite localizations. Sometimes it works, sometimes it doesn't work, and when it doesn't work and they all coalute perfectly, we still might try and use specific fragment ions to try and separate these things. But at the end, we always try to work with a combination of two, looking at the retention time of the peptide and looking at those specific transitions, and using these two pieces of information to pinpoint localization of sites. So let's go into an example. We go back to the peptides that we had before. We had these 3 options, and here we have 3 heavy peptides. Each one of them was spiked separately, and we scan through the B and Y ions. You can already appreciate that the peaks look somehow different. So you can say just by eye that there are different relative intensities, and maybe these are not exactly the same. So you would say, well, I can try and guess which one. But when we mix all of them together, they are also separated by retention time. These are very small shifts in time. You see it's maybe half a minute or so, but also very consistent. And whenever we would inject these three together, they would always keep the order of their elution, and they would keep, to some extent, when we use exactly the same gradient and so on, the space between these things. And now we're going to use first what happens to the transitions, and B, what happens at the level of retention time. So here they are very nicely separable, and in theory we could quantify each one of them separately. Again, I remind you, we are only considering here the case that there is only one phosphosite per peptide. So maybe a doubly phosphorylated will be somewhere completely different, and this will start to be even more complicated. Now we go to the other peptide where we had 5 different options. We prepared the different, we have heavy peptides for each one of these. Again, you can appreciate from the colors without the, I didn't put here legends, but you can appreciate that these maybe look different, and when we mix them, it gets a bit more complicated. So suddenly, these two seem to somehow coalute. This one looks a bit like a bump. This one that is, go figure out where it is, and this one, yeah, it's a bit of a mess. And this is here also a very short gradient. It's at the beginning of the gradient, so it's also maybe they will shift a bit in time. So trying to separate these is going to be hard. There are different things that we could do to try and optimize, or maybe change a bit the chromatography to make them more separable. But in this case, as we look at it like this, they're not really separable in retention time. But what we can say is that maybe if we look at the transitions, so we go back to that slide and we think, let's look at the transitions, maybe we can separate them by transitions. And what we also need to think once we see pictures like this is, before we would tell you, hey, why don't you just remove this interference? It's quite an annoying peak and it disturbs our quantification. In this case, this is not an interference, this is the coelution, or not a coelution, but the nearby elution of a separate phosphoform that is actually representing some biological information potentially. So we cannot just remove it or ignore it or say, well, that's just an interference for something else. It is something else. It's another phosphoform on the same peptide. So when we look at these sequences again, and we look at, in this case, only the Y ion series, you will see that, for example, Y5 is good to separate serine 24 and 25. Those were the two ones that, sorry, here we had the problem that we cannot separate 24 and 25, but when we look at these two phosphosites, the Y ion that would make the difference is the Y ion that has a different mass between the two, meaning including or not including phosphorylation site. And then we can just have a look at this Y ion of interest. When we look at it at each one of these spiked in separately peptides, we would see a peak in each one of these. We would not see it in 25. And so if we extract this, we can say, well, this is serine 24. And if we go now and extract the Y5 that is relevant for serine 25, we would get the complementary picture. So now we can say we can separate between 25 and 24. At least we can see a difference when it comes to the transition. Maybe it will be a bit risky to quantify only based on one transition, but at least we can say, well, we have some tool to look into the data and really mine the transitions and try to find those pieces of information that will help us to say which one is the right peptide that we're quantifying. And then we've done all these things with the heavy peptides, and we go to endogenous samples. And when we go to endogenous samples, and here you're already used to seeing this, we have a light and we have a heavy. In this case, the endogenous is in red. And you saw the distribution of the 3 phosphoforms, but actually in endogenous level, we only have 2 of them, serine 72 and serine 75. And serine 70, at least in the conditions that were measured here, does not appear to be actually there. And so we could suggest that it's actually maybe even was just a mistake from the search engine, or maybe there was another reason for why it was selected, or maybe it was in another sample and not in this sample. But we can now really go and quantify heavy to light ratios for each one of these phosphoforms and make sure that we get a relative quantification only for the right phosphoform and not making mistakes with selecting the other one. And you see how easy it is, or how tempting it would be here when we don't have a heavy form to sometimes make mistake and choose this one instead of this one if we would only see the endogenous and not see the light. And I'm going to show you an example in a moment. And I just want to tell you that all these findings about the different phosphosites were also afterwards validated by point mutation, so it was shown that these are only the correctly phosphorylated sites. This site was actually not affecting the phenotype of the yeast, and here I told you maybe there was one mistake about the serine 70, but remember that there were also all the double phosphopeptides in the combination, so probably there were even more mistakes in choosing all the combinations that included serine 70 and maybe were not actually correctly identified. And now let's look at an example. We want to hunt a certain site of interest. It's a certain protein we're interested in. We extract a certain set of transitions. We see a nice peak group. We say, well, maybe that's the site. We go and this is, let's say, based on shotgun data, but when we look at the heavy, we see that the heavy is at a different retention time. It has a different set of, a different relative intensities, and with the data that I've just shown you, we can say, well, it might be the same phosphosite, there might be the same phosphopeptide, but not the same phosphosite. It elutes at a different time, has different relative intensities, and what I would do now is look into the transitions. So I would look at the list of transitions and try to see, well, which are the transitions that I need to look at in order to pinpoint the site. Does somebody want to tell me which ones are those? The site is located here. The reference peptide tells me that this is the site. This peptide tells me else. If you just look at a sequence, which Y ions do I need to look at to know where is the site? Is it on this one? Is it on this one? Speak up.
Y5.
Y5. Is it the only one that I need? Y4 and Y5. Very correct. If I look at Y4 and Y5, in the heavy reference they correlate perfectly. In the peptide that came from the endogenous sample, there is no Y4, and I can tell you that it's, so the phosphorylation is actually happening one side to the right of the sequence, and this is, in this case, the wasted heavy peptide. I'm not going to be using it for quantifying this site of interest because I ordered it on the wrong localization. In this case, I also want to again stress the point. The times are very, very small. This is estrogen and the gradients are very short. In this case, it would be very easy when just looking at a group and not having a library. I also hid here the library to make a mistake and say, well, there's a super nice peak group, but in this case, it's for the wrong phosphoform. Sometimes the times are bigger, and then maybe you can, there are differences in retention time, and then you can maybe make use of this data, but in this case, it would be kind of marginal if we had only, let's say, a predicted retention time. Although I promote using heavy references, they're not always perfect. Sometimes they're actually very bad. This has to do with the chemistry of how they're synthesized and purified and cleaned and delivered to you. But one has to remember that not in every heavy peptide that you get, and this is more pronounced with phosphopeptides, you will have only one peak group to use as a reference. And what you see here is a spiking of a heavy peptide into the machine, and I get all these peak groups. They would probably have at least two of them the same relative intensities. They have different retention times completely, so it's very complicated now to say what is the predicted retention time, and most importantly, you have no idea which one is the right one and which one will correlate with the endogenous. So I always say heavy references are super useful, and sometimes they are actually quite complicated to use. I bring this, it's not a very common case, it's actually quite rare, but I prefer to show this slide so that you know that sometimes it gets complicated also using the heavy reference.
Do you have any ideas? What can explain this? The crude peptide, what could it be?
So if this was peptide lost to phosphorylation, then it would be in a different Q1 window, so it would not be targeted.
Different phosphoform.
So it's a crude heavy peptide. We would like to hope that the company knows where they're putting their serum. The reason is just, it's a very relevant question. The phosphorylation is added as a phosphoserine, so there's only one place in theory it could be added. Okay.
But maybe they completely messed up their synthesis. Could be one reason. What else?
Order of amino acid inside the peptide could be
The amino acid?
The
Sorry?
water.
and order of amino acid sequence is all the same, but can be some mistakes in the sequence inside.
So you're saying it's the same Q1 mass, but they shuffle the sequences. I again would like to hope that they don't randomly shuffle sequences. So if they're different length, they would have a different mass, they wouldn't pass the Q1 filter. Think of miscleave would not pass the mass filter. Sorry? Degradation would not pass the mass filter unless it's an in-source degradation. Rearrangement of the phospho is an interesting theory. There's been many acclaimed possibilities that phosphors jump from one to the other. I don't know.
Could be one explanation. But
I'd like to remind you that this is SRM and we have used a window of 0.7. So what happens with a window of 0.7? Isotopes. But this you would cover for the main one. They shouldn't drift in time and things like this. Sorry?
They might be over-fragmented after the Q1 window.
So after the Q1 window, there's a lens and they go into the... So there's... But what can happen, that is to some extent correct, is that they are arriving at different times to the Q1 window. For what reason? You're saying nearly isobaric peptide, so it's...
Yeah, because it's...
I would take it as that have a very, very similar mass. What type of modifications do you know that are very, very small?
The C13 and C12. If we have not totally 100% of C13 or nitrogen 15, you can have a mix.
But this would not affect the retention time. This would be right if that was a deuterium kind of labeling. This would affect retention.
Deamination is 0.9.
Deamidation.
Deamidation, very good.
First one, we have a modification that is when we divide it by 2 or 3, the charge state, we will get a modification that is actually within the window of the Q1, but it affects chromatography, so they elute at a different time. And in this case, we have a peptide that has a group that can go through deamidation, and then we would get different forms. What else? Which modification on a protein and a peptide has a change of 0 in mass? Sorry, I think I heard it. That's true, but again, we trust the company that they gave us. And in this case, that might be relevant if they put something else, but in this case, it would not apply. But which residues do we have here? This, for example, when we go in a circle around, methionine will create a mass difference. So proline. Proline can isomerize, and when you synthesize a peptide, it can come as a cis or a trans. This affects retention time, but it's exactly the same mass. There is no way of separating them by mass. This, in this case, is not a proline, and we see that whenever you have a proline. And what is very useful when you order these synthetic peptides, some of these companies will tell you, be aware of ta-ta-ta-ta, because you have a lot of N's or E's that can form problems, or you have prolines, etc., etc. Read the warnings. They're useful. But we can continue trying to think about different options, another option that we would like to mention is that what can also happen is that there are protection groups when these peptides are synthesized. These protection groups can, to some extent, remain during chromatography, but then be removed during the source fragmentation. During some in-source fragmentation can happen, the group is relieved, they would have the same Q1 mass, but at the level of retention time of the chromatography, they look a bit different. There are different explanations, but...
Yeah, but this, I think, is the most likely explanation for most of the things that we see.
But the Q1 is the same, the mass for Q1 is not the same.
Yeah, but
the mass would be the same.
It would be the same.
but only because during the ionization process. So as
Okay.
long as they are on the column, they are still carrying their protection group that you had throughout the synthesis. In the moment when they come off the column, they get ionized, they get this energy, they lose this protection group, and in that moment, it's exactly the same molecule. They are all exactly the same molecule, and this is why they all look exactly the same in terms of relative transition intensities. And the first example, I think, is most likely this example. You see all these groups, all exactly the same intensity, so you always see in the mass spectrometer you have exactly the same molecule, but when they were on the LC, they were somehow different. And this is something, yeah, that I think is the most likely explanation, but there will be a mixture of things why you sometimes see several peaks.
And importantly, when you use these things, you need to think of them in advance. If you're doing, for example, scheduled SRM, you don't know which one is the right one. If you're going to do a very small window, you might be measuring around a certain peptide, which is chemically the right peptide, but not the one that has exactly the same properties as the one that you are actually interested in. So this is a side note, but an important one if you're going to be using heavy peptides and suddenly you start to see weird things. So if we are going to be using these heavy references, I just want to summarize some points that I mentioned. When you think about peak boundaries, how we define interferences and transitions and which ones are useful and not useful, rethink how you define your peak boundaries. Sometimes you want to consider these interferences if they are related to something you're interested in, and which transition you remove is kind of complementary to this. If you kick out too many transitions, or you selected only the top 3 for quantification, and then you get at the end a lot of peptides, and you actually wanted to separate, and sometimes you would like to add a few more informative transitions. And when you use synthetic peptides, you use the retention time, and you use these unique transitions. The combination of all these 3 tools are very, very helpful to try and pinpoint your phosphorylation site of interest, but sometimes these themselves can be problematic. And what I would also like to stress is even when you're using synthetic libraries, and if you go through the pipeline that we showed you, then you also these first do SRM trigger MS2 or any type of other workflow, and then you go to a search engine. We already talked about it on the second day. Sometimes the search engine will give you a mislocalization compared to what you actually injected, and then you need to see how to adjust the PEP-XML so that it is correctly localized or not. So you need to try and understand, and sometimes you will not get something, a phosphopeptide, into your library simply because it didn't come up from the search engine as the correct localization, meaning correct as the one you ordered. That is what I refer to. And in this respect, there is also, here, to avoid the use of search engines, you can also do chromatogram-based libraries, but this is going to be Brendan. You're going to talk a bit about panorama. There are other options without search engines. Okay, so this was, the first case was when we have a reference. So we ordered the synthetic peptide for the site of interest, and we now know that sometimes they are separable by retention time, and we hope that this is actually, or we presume that this is most cases, but not all cases. And we know that these differences can be big or small. And now we want to go to the next step, which is when we're using only shotgun data. So this could be, for example, if we're doing a data-independent acquisition, when we use a library that came only from shotgun. It can also do when we're doing an SRM experiment and we first want to try and quantify some peptides label-free, and before we select which ones to order and which ones not. So in both cases, we only have shotgun data, and we don't know if this shotgun data is correct or not, but we're going to be we're going to be relying on it, and what I want to say already at the start is when you rely on shotgun data alone, this can create a lot of complications in building the correct library and then using it to extract, whether it's in SWAT or in SRM, to extract or to acquire the correct phosphoforms that we're interested in. I'm not going to talk here about how to build a library. This is going to be Ludo's talk. I'm just going to mention that in the case we saw before, if we would now want to build a library, or whether in, for SWAT or, for example, in Skyline, all of these will go into a library, and we will then try to, if we don't think about it, to acquire all of these in SRM or to extract all of these in SWAT. And the thing about SWAT or any type of targeted extraction method, that we're also going to extract all of these. And basically we're going to extract here several peptides. Some of them may not be correct peptides, as I've shown you before. One of them actually doesn't exist endogenously, but if we create the assay and we don't think about all the considerations that we discussed, there will be some assay and it will extract some transitions as coeluting, might be just the neighboring phosphoform that we're extracting. So we need always to remember this issue of retention time that might be that might be an issue, and then we need to think how we translate this from shotgun into SRM or SWAT. To make the case more pronounced, I'm going to be talking about SWAT data from Ludovic, and I'm going to be talking about this transition from a shotgun kind of approach to a SWAT kind of approach, and when we're doing this transition of quantifying in shotgun and quantifying in SWAT, and what happens. So let's take a case like this. This is the elution of a certain peptide of interest, and we had a shotgun event. We identified this site as the localization, and now we say, well, this localized peptide is eluting on this peak. This was in some shotgun run. We have one site identification, one peak. And this is very easy because we're going to have a nice identification. If we were doing shotgun MS1 filtering quantification type of approaches, we would have one area. And if we wanted to build from this a library in order to do SWAT, we would have one identification, so it's easy. And so when we take this and kind of transfer it to the SWAT concept, everything will be identified and validated, and we'll say that's fine and continue. Now, what also sometimes happens in shotgun is we have on chromatography only one peak, but then let's say at the beginning of the at the beginning of the peak there was an identification on this side, then there was the exclusion of the shotgun, and then at the end of there was another shotgun event, and this time the search engine assigned it to another site. So now we have two sites assigned to one chromatographic peak. Now this will create some problems for us, because when we look at the list of identifications, we actually have more identified peptides than peaks. So if we believe that all peaks are separable, then one of them should be somehow mistaken. If we try to quantify this peptide, well, imagine now that you have a matrix and then you try to do some sort of matching, and depending on which software you use, sometimes you'll be matching this peptide across several runs, and sometimes you'll be matching this peptide across several runs, and you'll have missing values for the other things. So the whole quantification will be full of missing values because we're trying to match different identified peptides. Some software tools consider these as two separate entities, so it really depends which one you're using. And if we're going to try and generate a library, here we're trying to generate two assays, but they're actually, from a point of view of SWAT, for example, they're just one peak. So at the end, we will extract only one peak. It is in a way convenient because this will reduce the list. So when we go from the shotgun data set from a library into the SWAT, we will reduce, you already saw it in Rudy's presentation, we will reduce the numbers to the number of these co-eluting peaks that we can identify, and somehow might be also able to try and resolve it and try and say which one is the right one, but this is not always the case. Sometimes we will not be able to separate and say, well, this was the correct one, this was not, depending again how we set our assay, but at least we will be able to say, well, at least there's only one peak to quantify reliably across our data set. And this is just an example. I'm sorry, it's from PeakView, it's not from Skyline. But we have here two peptides. if you look, there are it's a doubly phosphorylated with 2 localizations, but when it was extracted by Ludo in peak view, there's only 1 peak, and then we can try and figure out which one is the right one. Now there's another case which is also very problematic. We have 2 LCMS peaks, so these, we would argue, are actually 2 different localizations, and if they are sometimes assigned to the same sequence. So now one peptide supposedly, according to the shotgun result, eluted twice, but we suspect that these are actually 2 different phosphoforms of the same phosphopeptide. And if we go a bit faster, now we will be missing phosphosite identifications. We will have conflicts because sometimes we will quantify this peak, and then in the next run we will try to match it to this peak. They might be very close, as I've shown you before. They might be very far, but we might start to having mistakes, which is the right one and which is the wrong one. And basically we're going to be creating also a wrong library. And this will be due to the fact that if we now try and say what is the right assay and give a certain assay retention time, we told you retention time is very important. If we try now to average, the retention time actually comes somewhere in the middle between these 2 peaks, and there is not this one and not this one. So we somehow need to decide, are we going to quantify this one consistently or this one consistently and somehow separate them? And this creates a big problem in SWAT where we need to make these decisions and separate these peaks, not in order to avoid mistakes when we're quantifying 2 different peaks across runs. And here's an example where we Ludo extracted 1 phosphopeptides, but it gave 2 peaks, and then we can afterwards try and resolve which one is the right one. Here's another example, and you can see that here the separation in time is already quite considerable. So you can have different cases where you think you're extracting 1 peak, you actually get 2, but it has also a very big advantage. So it's not necessarily a disadvantage, because then we can consistently, once we handle this situation and are aware of it, we can very consistently quantify each one of these peaks separately. So let's just call this one peak number 1 and call this one peak number 2. And they belong to the same phosphopeptide, but they have 1 phosphorylation somewhere along the site. And in this condition, they would look like this, and we would follow them very consistently across time. We would see that in a certain condition, both of them go down. In another condition, just one goes down, and the other looks kind of similar. In a different condition, this peak goes up, and the other one goes down, and so on. So when we are aware of this issue, we can quantify them very reliably and actually make statements about which one is the one that is actually regulated without having mistakes of these run-to-run matches. And the fourth case is a variant of the third case, and that is when there's kind of what we called before an interference, but it's actually 2 phosphopeptides that are nearly co-eluting but not completely. And then again, basically we get 1 identification, but we suspect that there are 2 underlying phosphoforms of the same phosphopeptide. And here we're missing 1 ID. We think here there should be actually another one. And what happens at the moment when we do this extraction is we actually extract only 1 best peak group, and we might completely miss the other one. And at the moment we can also not suggest what was the other one, but this might be possible in the future. And this is again an example from peak view where we have this kind of shoulder type. We would suspect that there's another phosphoform here, but if we would just go and extract, we had 1 assay, we extract 1 peak, and we don't know exactly how to handle this one at the moment. Now back to this example, once we've done this quantification, we've quantified the peaks correctly. You remember I told you, let's use also the transitions. And in data-independent acquisition, as Ludo have shown you, we can go back to the data, reiterate, and try to extract those transitions that we're interested in. So as we did before, we said let's take Y4 and Y5 and measure them both. We need to think about it a bit in advance before we do the measurements. And if we do a targeted extraction of the data, we can first quantify all the peaks, and then in a second iteration try to extract those transitions that are most informative for the localization. And this is very useful, something that you could do in SWAT, something that you can do also in PRM, for example. When we do 1 step of peak quantification and 1 step of extraction of unique ion signatures, unique ion signatures are those combinations of transitions that will tell us, aid us in localizing the site of interest. So as we've done before, the little example with the Y4 and the Y5, we need the combination sometimes it's you only need one, sometimes it's 2 or 3 fragment ions of interest that will allow us to pinpoint the phosphosite of interest. And this is what we saw before. So I tried during this talk to give you a few examples of how we target modifications. And I told you that when we want to look at specific phosphosites, we need to, we can do it in high confidence, whether we're doing SRM or we're doing SWAT, but we need to take some precautions and steps. We need to be aware of the advantages of synthetic peptides. We need to be aware of the advantages of having shotgun data in the background, but there are also pitfalls where we can run into, and then, for example, we ordered the wrong phosphopeptide because we didn't consider all of these options. And the chromatography here is a real helper. Many times we can separate the peaks. In cases that we not, maybe we want to consider how to actually separate them, maybe change something in our running conditions in order to make them separable. And if they are really separable, then we can use this retention time information as we've done before in the tutorials, but here in this case for the localization of a specific phosphosite of interest. And when we do these on a large scale in SRM, maybe we can order 1 or 2 or 3 peptides and really try to, when we're working with specific proteins, but when we go to SWAT type of applications, when we have thousands of these sites across many runs, we really need to be extra careful in how we build our library and how we take into account retention time so that we don't make these mistakes and carry them over many, many files and runs and get an incorrect data set. Exactly how to do these steps, to some extent Ludo will discuss, and some of it is still under development, but I just want to bring to your attention in this talk that this is a critical issue that you need to take into account right from the start. And then there are also some extensions to this, and that is, as Ludo very briefly mentioned, sometimes when we use data-independent acquisition, we can also try and take it to our advantage. So we can try and take shared transitions and using these shared transitions to extract modified and unmodified peptide. Let's say in the case of phospho, they would maybe come out in different swath windows. But for example, if we take these two peptides, one of them is phosphorylated and one of them is not, if we would extract only this Y ion series, they are shared between these two forms. And if we didn't look at the MS1 level, we would just extract 2 peaks for the modified and unmodified version. And this could be a problem if we wanted to find only the unmodified one, but it could also be an advantage because now we can actually try and detect these using information that we have about the unmodified version. It can also be a problem when there are modifications that we didn't consider or didn't think about. They fall within the same window, for example, oxidation, and then we would be extracting one hoping only to find a certain peptide of interest, and we're actually extracting 2, the modified and unmodified version. There could be very different modifications that we don't even know what they mean, and we still get more than 1 peak. This is a difference between SWAT and SRM. In SRM, since we have the first filter that is fairly narrow, we can pinpoint it to small modifications, as we've discussed before with the synthetic peptides. In SWAT, we have a much bigger window on the Q1, and therefore we also have to start considering many more options of what could be happening to this peptide that would affect or create these results. So whenever I've shown you before that there are 2 phosphoforms, in theory one could consider that in a certain game of sequences this could also be one phosphoform and the other is the oxidized version of this same peptide, etc., etc. So there are more combinations and things to consider depending on the specific sequence and all the information that we've collected about retention time, relative intensities, and so on. With that, I would like to finish. I hope I am almost on time, and ask if you have any questions.